Welcome back, ladies and gentlemen. Today we are going to be talking a little bit more about bonding, especially ionic bonding. In this case, we're going to be trying to reverse engineering the process that we've learned so far. So far, we've begun the process where we have the ion species that make up the compound. We figure out what the formula of the compound is, and then we write the name. That's what we've been doing thus far. But what we want to do now is we want to write correct formulas from the names. So we want to get the names, and in order to do that, we first have to determine the ions needed to make up the bond given by the name, and then we have to use a method, one of the three methods, to find the correct formula. Now I say one of the three methods because in this particular case, if we have polyatomic ions or D block metals, we can't use the dot structure method. So we're just going to skip it right now. Remember, it falls apart, so we haven't been using it very much lately. So the first example is going to be a visual plus minus method. Remember, this works with every combination that we can have. So when we look at the visual plus minus, we're going to be getting a little bit more here. So let's see. What if we have stannous hydroxide? Okay, so what we need to do is we need to look at our information. On our purple sheet, we have some names, and those names are for polyatomic ions, which includes this guy over here, and we also have names for some D block metals that might be useful for us. So if we look up stannous, we'll find that stannous means SN2+. Okay, so that's the first part of the name. The next part of the name is hydroxide. Well, SN2+ and hydroxide is OH and O and H with a 1- charge. So now we're going to use the visual method. Now that we've gotten and produced our ions, we can now take those ions and make a formula from them. So we have 10, and that 10 has 2+ charges for everyone. 2+ charges want to be given away. OH group has a minus charge. It wants to accept an electron. So this electron is accepted by OH, but 10 is still not happy. So we have to have another OH, and that OH comes in and accepts another electron. And now we can see all the electrons needing to be given away are given away. All the electrons that need to be accepted are accepted. So the formula for this compound is SN, just one of them, and we have a group, OH. So we have to be really careful and stop and say, okay, let's put the group in parentheses, the whole group and nothing but the group. And then because we have two of them, we put that on the outside. So we get SnOH2, and this is the answer for what is the formula for stannous hydroxide. So that's what we're trying to do. We're reverse engineering. So we're starting with the name. We're going back to the ions, and then from the ions we figure out the formula. Before, we were starting here, getting to this, and then going to this. Now we're starting here. Let me get another color here. Okay, now we're starting here. We're going here. We're going here. Sorry. Starting here, going here, and then we're getting to this. So a little bit of a reverse engineering. We're starting from the top and going down. Before we started in the middle and went down and then went back to the top. Okay? So let's try another one in a different method. So let's try this one, sorry, in the least common multiple method. The next one I want to do is hydrogen phosphate. And I'm going to tell you that this guy has another name. It's actually called phosphoric acid. Phosphoric acid. So when we look at this, we have a couple cues here. First of all, you're going to say, well, Ms. Stover, these are all nonmetals. What are you talking about? Well, you guys have been asking me why hydrogen is all the way over here on the periodic table, all by its little lonesome self with these metals. And it's because of the way hydrogen behaves in acids. When hydrogen is an acid, especially when hydrogen is the first substance in the compound, hydrogen behaves with a 1 plus charge. That's what we know about hydrogen there. Now, if hydrogen is not the first substance, or it doesn't say the word acid with the name, then we do not treat hydrogen like this. We treat hydrogen like a nonmetal, and we let it bond covalently. But when hydrogen is first, or you see the word acid, we're going to know that hydrogen is going to be an H plus here. Sorry about that noise. Okay, so what we've got is phosphate. So we're going to be looking at our polyatomic ion sheet because it ends in 8. Phosphate, we notice, is a 3 minus charge, and it's a PO4 3 minus. Okay, so the least common multiple method says I need to know the least common multiple method between 1 and 3. Not the 4. The 4 is with the O in the PO4 group. That's my group. So once again, I'm just going to reiterate, this is the group. I cannot change the group. I have to always keep the group just like it is. So the number I'm worried about here is 3 and 1. So the least common multiple between 3 and 1, the number that they both go into evenly, is 3. So we need to lose 3 electrons. We need to gain 3 electrons. So to get a 1 to be a 3, we have to multiply by 3. To get a 3 to be a 3, we multiply by 1. So we get H3. And then because PO4, because there's only one of them, I don't need parentheses. I just need to write PO4. So now you know the formula for phosphoric acid is H3PO4. So one more example here. Let's see if we can come up with another example to do in the next one. Okay. So the switcheroo method, remember, it falls apart in places, and if you don't understand it, we can't use it, but let's see if we can use it for this one. Manganic oxalate. Okay, manganic oxalate. Well, this is sort of like the first one we did because we have 2 species that we can look up on the purple sheet. The first one is manganic. Manganic is manganese, Mn. But it's manganese with a 3 plus charge. That is manganic. Then we look up oxalate. Oxalate is a polyatomic ion. How do I know that? Well, I see the 8 ending. Most of the time when I see an 8 or an ite ending, I'm looking at the purple sheet, the polyatomic ion sheet that I've been given. So when I look that up, I get C2O4 2 minus. That's 2 carbons and 1 oxygen. And let's say that again, that this is our group. We cannot change our group. We must keep our group the same. We cannot do anything about that. So here we have a 3 plus and a 2 minus. The switcheroo says the 3 becomes the number of the oxalates, the 2 becomes the number of the manganese, and I get Mn2. And remember, I got to keep my groups together, so if I have to have more than one of them, if this is not a 1, I've got to put parentheses, everything in parentheses, with the 3 on the outside. And there's the formula for manganic oxalate. So you can see in this particular part, we're trying to reverse engineer a little bit. We're starting up here with the name, so we're starting right here. We're moving down to here, and this is our second step, determining the ions, and then we go down here to the formula for step 3. And if you'll recall the last time we did this, or when we were looking at it before, this is where we started. This was our number 1 step. We would then go down here to the formula to number 2, and then from there we would go back up to the name. So we're reverse engineering a bit. We're just reordering and trying to restructure. So hopefully you're going to be doing okay here. If you need any extra help, please feel free to see me.